All right, greetings YouTube, beautiful mind here. Let's see. So I hope everyone is doing well. Let's see. So we're kind of entering the home stretch. We have a few announcements that we need to discuss. Let's see. So one, I think I did go ahead and load exam 3. So we're kind of entering the home stretch. Let me see. So I'll do the best I can to get as many assignments loaded for the remainder of the quarter as soon as I can. I thought I made a point to go through and load exam 3 for all courses. Okay, so and it's not due this Saturday, but it's actually due next Saturday. So you actually get a whole week to work on that. You get unlimited attempts at it until next Saturday. Let's see. I think that we have an assessment that should be available on Moodle, so you want to definitely go ahead and complete that as soon as possible. It's going to count as a quiz grade. You get one attempt at it. So, and it's just for general questions, right? So you just want to be sure to get your assessment submitted. I think that's it. Just getting our assignment submitted promptly on Pearson, and we have that assessment on Moodle, and we're kind of and that's pretty much it. We're just kind of entering the home stretch a little bit. Okay. So today I'd like to go ahead and close out chapter 5 by taking a look at sections 5.4 and 5.5. So 5.4 is on sampling distributions and the central limit theorem, and 5.5 is on normal approximations to binomial distributions. So some objectives for this section: how to find sampling distributions and verify their properties, how to interpret the central limit theorem, and how to apply the central limit theorem to find the property of a sample mean. So sampling distribution is the probability distribution of a sample statistic that is formed when random samples of size n are repeatedly taken from a population. Okay. If the sample statistic is the sample mean, then the sampling distribution is the sampling distribution of the sample means. Okay. Okay. Let's see here. The sampling distribution consists of the values of the samples x1 bar, x2 bar, populations with the mean mu and standard deviation sigma. A random sample 1, so we have these sample means. So this is just taking samples from a population. Okay, let's let that mean. So we have the average of sample means mu x bar is equal to the population mean mu. So the mean of the sample means is going to be equal to the population mean. Okay, that's just one of the things we have. The standard deviation of the sample mean is equal to the population standard deviation, okay, divided by the square root of the sample size, n. This is called the standard error. So the standard deviation of the sample means is the population standard deviation divided by the square root of n, okay? So again, the mean of the sample means is equal to the population mean, and the standard deviation of the sample means is equal to the population standard deviation divided by the square root of n, okay? And again, this is called the standard error of the mean, okay? So let's look at this example. Sampling distribution of sample means. The number of times 4 people go grocery shopping in a month is given by the population values 1, 3, 5, and 7. A probability histogram for the data is shown. We randomly choose 2 of the 4 people with replacement. List all possible samples of size n equal to and calculate the average of each. These means form the sampling distribution of the sample means. Find the mean, variance, and standard deviation of the sample means. Compare our results with the average with mu equal 4, variance sigma squared is 5, and the standard deviation is sigma, which is going to be the square root of 5, which is approximately 2.2. Okay. So all possible sample size, let's look at this one more time. Number of times that people go in a grocery store in a month are given by these values. Okay. 2 of the 4 people. List all possible sample size. So, you could have 1, 1, 1, 2, 1, 3, 1, 4, 2, 1, 2, 2, 2, 3, 2, 4, so on and so on until we do all of them. Let's see. So we see this here. So, you can have 1, 1, the person, 1, 1, 1, where's 1, 2? I don't understand why they didn't do 1, 2, 1, 2, 3. Oh, because 2 wasn't there, right? Yeah, 1, 3. Yeah. Okay. 1, 1, 1, 3, 1, 5, 1, 7, 3, 1, 3, 3. Yeah. So all the combinations just, but the first person chose the first one, second one chose the second. And then find the average of each sample. So the average of 1 plus 1 divided by 2 is 1. 1 plus 3 divided by 2. So that's 4 divided by 2 is 2. 6 divided by 2 is 3. 8 divided by 2 is 4. So we're just basically taking the average of all of those samples. So then we get the sample average, okay? So then, so then for the probability distribution of the sample means, so on the far left we have our averages, which is the X bar. So we have the average was 1, 2, 3. So we list out our averages, and then we count how many times they occur. So the average of 1 occurred once, right? You see it here. The average of 2 occurred twice. You see them on the left column. So on and so on. So we're counting each time the average occurred, and we had a total of 16 averages. So then, or the frequencies add up to 16. So then you just say each one divided by 16 to get the probability, and then we graph the probability. Okay. So then I think it said that the sample mean is the population mean. So it's going to be 4. The variance of the sample mean is going to be, it should be, you have to, let me see something. Ouch. I want to see. I mean, we introduced a thing where we said it's going to be, the standard deviation is going to be, let me see, I'm just trying to get, the standard deviation of the sample means is going to be the population standard deviation divided by the square root of n. So if we want the variance, we square that, right? So then that's how we get the 2.5. Yeah. Okay. Okay. I'm going to let this be for now. So if sample sizes of size, let me see, if the samples of size n greater than or equal to 30 are drawn on any population with the average mu and the standard deviation of sigma, then the sampling distribution of the sample means approximates a normal distribution. Let's see. Any population distribution. Then if we look at the distribution of sample means, as long as n is greater than or equal to 30, then it's going to be approximated by a normal distribution. Okay. If the population itself is normally distributed, then the sampling distribution of the sample means is also normally distributed for any sample size n. So if the original has a normal distribution, which is the bell-shaped curve, then when we find the sampling distributions of the sample means, that's also going to be a normal distribution for any size n. In either case, the sampling distribution of sample means has a mean equal to the population mean. The sampling distribution of sample means has a variance equal to 1 over n times the variance of the population. And the standard deviation equal to the population standard deviation divided by root n. Okay. So let's see, a study analyzed the sleep habits of college students. The study found that the average sleep time was 6.8 hours with a standard deviation of 1.4 hours. Random samples of 100 sleep times are drawn from the population, and the mean of each sample is determined. Find the mean and standard deviation of the sampling distribution of the sample means, then sketch a graph of the sampling distribution. 100. So notice that 100 is larger than 30. A study analyzed the sleep habits of college students. The study found that the average sleep time was 6.8 hours. So then that means our mu should be 6.8 hours. And our standard deviation, is going to be basically that divided by 10, so it's going to be 0.14. Then sketch a graph of the sampling distribution. And it should just be a bell-shaped curve with the mu is 6.8 and the standard deviation is is going to be 0.14 hours. Let's see, how do we do? So we got the 6.8, and our standard deviation is going to be the population standard deviation divided by root n, so we get a 0.14. Again, a bell-shaped curve with the average at 6.8 and a standard deviation of 0.14 hours. Okay. Okay. Hopefully I didn't get overzealous with trying to get 2 sections in today. Let's keep going. What's my time looking like? Oh, we've only been going for like 10 minutes. Okay, we should be fine. It says the training heart rates of all 20-year-old athletes are normally distributed. So we're given that it's normally distributed with an average of 135 beats per minute and a standard deviation of 18 beats per minute. Random samples of size 4 are drawn from this population, and the average of each sample is determined. Find the average and standard error of the average of the sampling distributions and sketch the graph. Okay. So our average is going to be the same. So the average should be 135. I think the standard error is going to be the population standard deviation divided by the square root of n. Is that right? Let me see something. I'm just looking at my standard error formula again. Yeah. Okay. So, and our n is 4, so we're going to say divided by 2 because the square root of 4 is 2. So it's going to be 9. Standard error should be 9. Mu should be 135 and the standard error should be 9. Okay. All right. So to transform x bar to a z-score, is going to be x bar minus the average of the sample averages. Basically, x bar minus mu divided by sigma. Oh, but then, our sigma, we have to adjust it for the standard error. So we got to say sigma over root n. Okay, that's transformed to a z-score. The figure shows the average distances traveled by drivers each day. We randomly select 50 drivers ages 16 to 19. Did we do 2 sections last time or not? I think we did. We randomly select 50 drivers ages 16 to 19. I may have skipped a section. I gotta go back and look at my video from last time. What is the probability that the average distance traveled each day is between 19.4 and 22.5 miles? Assume that the standard deviation is 6.5 miles. So probability. Okay. So we need the z-score. Let me see. So we need x bar. The figure shows the average distances traveled. We run to select 50 drivers. So notice that that's more than 30. So it is that means we can approximate it with the normal distribution. 16 to 19. So if our x bar is 20.7, we want to know what's the probability that is between. Okay, so we got to change. So, okay, let's do like this. So x bar is going to be 20.7, right? So that means our z-score is going to be, okay, let's go actually. That's not our x bar, it's our mu. Let me go like this. So we're the probability that x is between what? 19.4 and 22.5, right? So we have a mu is going to be the 20.7, and our standard deviation sub x bar is going to be 6.5 divided by the square root of 50, all right? So then the z-score is going to be so we have to find two z-scores, right? Because we want the lower, the left, the right minus the left, right? So the first z-score we're going to do is the 19.4 minus 20.7 divided by 6.5 over the square root of 50. We get an answer. And then we do it for the upper, and then we're going to subtract our two answers. We get our z-scores, and we have to look at the probabilities and then subtract them from the chart. Okay, let's see how. So I'm going to use this here. So the mu is 20.7, right? That's what we said. And standard, what is it called? Standard error, 6.5 divided by root 50. So then we got to find the z-score for each one. So we get a negative and a positive. Then we got to use the chart to get the two probabilities and subtract them. So the 0.9750 and the 0.0793, those came from the chart like last time. And then we say the larger minus the smaller to get the probability. Okay. I don't know if I can make it through another one. What's our time? I guess if we've been going for 20 minutes, I just need to keep going. We're almost done with this section too. It says, so this is on finding probabilities for sampling distributions. It says, the average room and board expense per year at a four-year college is $10,453. We randomly select 9 four-year colleges. What is the probability that the average room and board is less than this? Assume that the room and board expenses are normally distributed with a standard deviation of this, right? So the question asks us, what's the probability that X is less than the 10,750, right? So then we have an average $10,453 and our sampling error, standard error, hope I'm saying that right. I need to just look it up. Is going to be standard deviation is 1650 divided by square root of n, right? 9, so divided by 3. Let's see, that's a 5, 15, 50. Okay. Oh, so then if we want that probability, first we need to convert it to a z-score. It's going to be that 10,750 minus the 10,453 divided by the 550. We get an answer, we get a z-score, and then we look at our chart and we find the probability. And since it's less than, we could just take the probability directly from the chart. Okay. So we get a z-score of 0.54. We look at the chart and we'll get a probability of 70, all right? We can just read it directly. That should come directly from the chart. How many more? Some college students use credit cards to pay for school-related expenses. For this population, the amount paid is normally distributed with the average of this and a standard deviation of this. I'm going to leave this in as an exercise for you all. If you need me to do it, I don't mind. I can walk you through it, but I'm going to leave this as an exercise. I'm going to kind of glance at it though. What is the probability of random selected college student who uses a credit card to pay for school is less than 1,400? So that one's similar to the last one that we did, right? We can identify our mu. We can identify our standard error. So we got to say the standard deviation divided by the square root of n. We convert the x value to a z-score, and we can pull the probability directly from the chart. The second one says we're randomly select 25 college students who use credit cards to pay. What is the probability that the average is less than this? Okay, and we're given that this distribution is normally distributed, so we don't have to satisfy that n greater than or equal to 30 thing. Oh, okay. And the first one, it looks like the first one is like the second one is a sampling error, but the first one is not, right? Because I was like, what's the difference between these two? The second one, we have the n is 25. The first one is just about the entire group, right? So the two the first one has a standard deviation. We just take the standard deviation. The second one, we got to do the standard error, right? So we have to do the two and then compare the two. So in this case, we're asked to find the probability associated with a certain value. Notice we just took the standard deviation, right? So we didn't have to do the whole divided by the root n. We get our z-score. Look at the chart and take it directly from the chart. Okay. For the second one, we're asked to find the probability associated with the sample average, the sample mean. So then we have to divide by the square root of n for the standard error. So the probability that the average credit card balance of the 25 card holders is less than 1,400 is about 2%, 2.5%. Although there's a 35% chance that the college student who uses a credit card to pay for school-related expenses will pay less than 14, there's only about a 3% chance that the average sample of 25 students will pay less than 14. Because there's only a 3% chance, this is an unusual event. I think we said it's unusual if it's less than 5%. Okay. Now that close it out. How much time? 24. Okay, so give me a moment. I'm gonna go ahead and load because my goal was to do 5.4, so I'm gonna just power through. I am a little bit exhausted. I just finished up another lecture. Give me a moment. I'm gonna go ahead and load the 5.5. All right, and we are back. All right, let's take some time to go through this next section. So this will be the last section for chapter 5, section 5.5, normal approximations to binomial distributions. So some objectives here are how to determine when the normal distribution can approximate the binomial distribution, how to find the continuity correction, how to use the normal distribution to approximate binomial probabilities. So normal approximation to a binomial distribution, if n times p is greater than or equal to 5 and n times q is greater than or equal to 5, then the binomial random variable x is approximately normally distributed, with the average is going to be n times p and the standard deviation is going to be, the sigma is going to be the square root of npq. Where n is the number of independent trials, p is the probability of success in a single trial, q is the probability of failure. So just to kind of backtrack a little, remember for binomial, we have a trial is repeated a fixed number of times. Each trial has only two possible outcomes, either success or failure. Each trial is independent of each other, and each trial has the same probability of success. I think there's like one more thing that I might be missing, but yeah, that's essentially it. Probability, and the random variable x represents the probability of success for each trial. Okay, I'm going to let that be. So we have the binomial distribution with the probability of success is 25%. The probability of failure is going to be 75%. We have 4, and then we're going to consider if we repeat the trial several times, like we repeat it 4 times, 10, 25, and 5, right? So notice that in each case, we're repeating this trial more and more times. We said that if n times p is greater than or equal to 5 and n times q is greater than or equal to 5, it can be approximated by the normal distribution. So if we look at the first one, n times p is going to be 1. Notice that's not greater than or equal to 5, and notice that that first chart is not really normally distributed. Let's try the second one. N is 10, so 1/4 of 10, 10 divided by 4, it's like what, 2? 2.5? So notice that's also not greater than or equal to 5, and it's not really normally distributed. But I think when we get to the next two, where n is 25, notice that np and nq are both greater than or equal to 5, and the binomial distribution is approximately normally distributed. Same for the third one. Okay. So as n increases, the histogram approaches a normal curve. So let's look at this example on approximating a binomial distribution. 2 binomial experiments are listed. Determine whether we can use a normal distribution to approximate the distribution of x. The number of people who reply yes. If we can, find the average and standard deviation. If we cannot, explain why. In a survey of 8 to 18-year-old heavy media users in the United States, 47% said they get fair or poor grades. See and below. We ran to select 45 8 to 18-year-old heavy media users in the U.S. and asked them whether they get fair or poor grades. So the question is, can we use a normal distribution to approximate this binomial? So we need to consider NP and NQ. So let's go like this. So let's see, our N (45), right? So our N is 45. The probability that they say yes is 47%. The probability to say no is 53%. All right. So notice that both of these N times P and NQ, they are both greater than 5. So this should be a yes. We can use a normal distribution to approximate the binomial. All right. Oh, and then this is the second question. We'll come back to that one. So notice that both of these are greater than or equal to 5. So we can use a normal. And then the standard deviation is going to be the square root of NPQ, which is approximately 3.35. Let's go back to the second question. In a survey of 8 to 18-year-old light media users in the US, 23% said that they get 4 or pair grades. We select 20. Okay. So in this one, notice that our N is 20. Probability of a yes is 23%. It's 23%. And so the probability of a no is, what is that? 77%. So 1/4, 20 divided by 4 is 5, but that's less than a quarter, so that's going to be less than 5. Notice that our NP is less than 5. The NQ is greater than 5, but the NP is less than 5. So for this one, we cannot approximate this one with the binomial distribution. I mean, with the normal distribution. Oh, that's the first one. Okay. Second one, notice the NP is less than 5. So we cannot use a normal distribution to approximate the distribution of x. Okay. Okay. A binomial distribution is discrete and can be represented by a probability histogram. To calculate exact binomial probabilities, the binomial formula is used for each value of x, and the results are added. I'm like kind of zoning out here. A binomial distribution is discrete and can be represented by a probability histogram. To calculate the exact binomial probabilities, the binomial formula is used for each value of x, and the results are added. Geometrically, this corresponds to adding the areas of the bars in the probability histogram. When we use a continuous normal distribution to approximate a binomial probability, we need to move half a unit to the left and to the right of the midpoint to include all possible x values in the interval. This is called the continuity correction. Okay. So now we're asked to use a continuity correction to convert each binomial probability to a normal distribution. It says the probability of getting between 270 and 310 successive inclusive. Inclusive means we can include the endpoints. So if we want to use a continuity correction, we need to go, let me think about this. Yeah, if we're going to include those endpoints, so we need to go half a unit to the left of 270 and half a unit to the right of 210. So half to the left of 270 is going to be 265.5. Half to the right of 310 is going to be 310.5. Okay. So when we calculate that probability, we need to do the correction for continuity. That continuity correction. Okay. Let's look at this one. This one is we want to use the continuity correction to convert. Okay, it says the probability of getting at least 158. So these outcomes are going to be 158, 159, so on and so on. So we need to go slightly to the left of 158. If we go slightly to the right, then we're going to be excluding the 158, and we want to include the 158. So then this is going to be the probability that x is strictly greater than 157.5. Okay. So this one is the probability of getting fewer than 63. So these outcomes, if we want fewer than 63, that means we're talking about 62, 61, 60, so on and so on. So that means we want to go half a unit to the left of 63. So then we're going to say this is going to be the probability that x is less than 62.5. You can say less than or equal to. Oh, strictly less than. Okay. That's fine. So when using the normal distribution to approximate binomial probabilities, verify that the binomial distribution applies. So specify NP and Q, so make sure that you're working with a binomial. Then determine if we can use the normal distribution to approximate the binomial by observing NP and NQ and seeing if they're both greater than or equal to 5. Then find that the averages, our mu is going to be NP, our standard deviation is going to be the square root of NPQ. And then apply the appropriate continuity correction, convert it to a z-score, use the chart. Okay. In a survey, 47% they get the fair. What is the probability? Okay, let me see how much I can do here. So X for the probability that X is fewer than 20. So X is strictly less than, not less than or equal to, fewer than 20, right? Strictly less than. Fewer than 20. Okay. So first we need to see, are we doing a binomial? So let's see, can we identify our n? It says 45. So we have 45. The probability of a yes is 47%. 47%. The probability of a no is 53%. Notice that NP is greater than or equal to 5 and NQ is also greater than or equal to 5. I think we did this earlier. Okay. So we can use the normal distribution to approximate the binomial. So then we need to do a continuity correction. If we want fewer than 20, that means we're going to subtract half a unit. So we want to calculate the probability that X is less than 19.5. Okay. So then from there, we should take that 19.5, convert it to a z-score. So that's going to be the 19.5 minus our mu. So again, our mu is going to be whatever n times p is, and our standard deviation is going to be the square root of npq. So you have to use a calculator there. So this is going to say minus mu divided by sigma. You get your z-score, look at the chart, and we can take it directly from the chart. Let's kind of move forward. Oops. No, I didn't know that was going to happen. Okay, then this is good. Less than 19.5. Okay. I'm gonna let that be. All right. So a study on aggressive driving found that 47% of drivers said they have yelled at another driver. We randomly select 200. Okay. What is the probability that at least 100 drivers? Okay. So let's just identify the components. Let me see. I just don't want that little thing at the bottom. Okay. So our n in this case is what? 200. Probability of a yes is 47%. Probability of a no is 53%. So that means our mu is going to be NP. Our standard deviation square root of NPQ. Okay. What is the probability at least? So we want the probability. What's the probability that at least 100 drivers will say yes? So X is greater than or equal to 100, but then we need to correct for continuity. Because we're using the normal distribution to approximate the binomial, if we want to include the 100, we have to go slightly to the left of the 100. So then we need to calculate the probability that X is greater than or equal to 99.5. So then we got to find the z-score. Is going to be that 99.5 minus the mu we have to calculate divided by the sigma we need to calculate. Okay. Let's see. So again, mu, okay, NP is greater than 5, NQ is greater than 5. We can use the normal, we can approximate the binomial with the normal. Our mu is going to be NP, which is 94. Our standard deviation is going to be the square root of NPQ, which is approximately 7.06. And again, correction for continuity. Now I did greater than or equal to. That needs to be strictly greater than 99.5. That's fine. Oh, so then from here, now if we want strictly greater than 99.5, we find the z-score. When we read the chart, we're going to get, when we get our z-score, if we want greater than, when we read the chart for the proper z-score, we're gonna have to say we're gonna have to use the complement rule. We're gonna have to do 1 minus to get the right hand side. All right. So we get this z-score. Okay. So then we got to say 1 minus the probability to get the right hand side. Okay. Let's try a few more. So we have a study on the National Football League retirees ages 50 and older found that 62% have arthritis. We randomly select 75 NFL retirees who are at least 50 years old and ask whether they have arthritis. What's the probability? Exactly 48 will say yes. Okay, we can do this. Let's see. What is our n in this case? 75, all right? Probability of a yes is 62. Let's write it like this. It's going to be 624. The probability of a no, if that was 63, 37.6. I think both of these, both NP and NQ should be greater than or equal to 5. I'm not calculating just for the sake of time, but I think that they are. Totally sleepy. Let me see. So you know how to find the mu, you know how to find the average. It says, what's the probability exactly? So now if we want the probability that x is equal to 48, we have to correct for continuity. So then we got to go plus or minus a half. So we want to calculate the probability, what is that? 47.5 is less than x, which is less than 48.5, right? So we got to find those two z-scores with the proper mu, proper standard deviation. Look at the chart and subtract our probabilities. Okay. So notice that both NP and NQ are greater than or equal to 5. You see the correction for continuity, and then subtract our two probabilities. So we have our z-scores. Find the two probabilities and subtract them. Okay. All right. So on that note, we're going to end the session here. Again, major thing is that assignments are posted. You want to get them submitted promptly and as soon as possible. I'm available if you have questions or if you need me to kind of go further in detail or redo any presentation. Also, I'm available for homework. I know the tutors may or may not be able to help with this, but so you know. But this is why I use Pearson, because Pearson is pretty good about having an explanation attached with each question, right? So as long as you kind of plan ahead, like I'm trying to give people enough time to kind of work on it, so you're not trying to, so we're not rushed or crammed at the end. Notice that the closer we get to like finals and things like that, the more the website will be like shutting down, and it's like it's going to lock up and not work. So this is why I try to load assignments as early as possible and try to give you ample time to get assignments submitted. Okay, I can't think of anything else. Also, just be sure that on Moodle, there is a assessment that we need to submit. Okay, so we need to submit that as soon as possible. On that note, again, we're going to end the session here, and from one beautiful mind to another, enjoy the rest of your day. Have a great weekend, guys.